Hey everyone, Thursday, going over regression modeling, talking about correlation and what we're going to do to try to find the correlation coefficient, things like that. I'm going to lead into doing the finding the line of best fit, probably Friday, and then go on from there. I'm trying to get into the point where we're going to start doing some um, projects where we're going to pick some data and try to find um, or pick some things and try to record some data and then figure out correlations and lines of best fit and make some predictions of data going forward. But again, we're probably about a week or two away from that. I just want to get through this unit and then maybe one more before we start doing that. So let's get on with today's lesson. Like I said, we're working with regression modeling. Going to cover some of the stuff we worked on the end of last week to kind of refresh our memory on that. So we're working with two quantitative variables. Remember, we're doing a relationship between two variables that are numbers. Um, so it's called bivariate data. It's data collected on two variables where each variable or each value of one variable is paired with the value of another. Um, so we'd be looking at like hours of sleep and results on a test. So we'd do different readings on that, comparing having a reading of the number of hours slept and then the person's score on the test. Again, we have an explanatory variable, which is the variable that helps explain the other variable, which is the response variable. So obviously the response variable is the variable that we're measuring to study or focus on what we're going to try to predict from that. A positive association, that's going to occur when both variables increase together. So as we kind of read it, if hours of sleep goes up, the score on a test goes up, then that's going to be your positive association. Obviously, a negative association then is going to occur when one variable increases as another variable decreases. So as hours of sleep goes down, I'm sorry, if hours of sleep go up and test scores go down, that's going to be a negative association. Probably be more associated with hours on the cell phone going up, test scores would go down. And then what we call the residual is like the leftover variation in the response variable and measures the difference in the actual variable versus what we would expect or predict that value would be um, based on the explanatory variable. So how we figure that out is when we finally get to lines of best fit, we're going to have a linear equation for that. And then we'd take our explanatory variable number. So suppose we had a variable where the number of hours slept in my example was 8 hours slept. We'd plug 8 hours into our linear equation for our line of best fit and we'd get what we would expect the score on a test to be. And the residual is going to be the difference between the actual score that the person who slept 8 hours got on the test and that expected value. That's what they talk about, the residuals. It's a little later on in the unit that we'll get to that. So what we're going to do is do some examples on identifying the explanatory and response variable. So example one, your teacher thinks there's an association between time spent on smartphones and GPA for schools. I want you to identify the explanatory variable and the response variable for that. And then example two, how does the amount of time spent doing homework affect students' test scores? Again, I want you to identify the explanatory variable and the response variable for that. Okay, so we've gone through, we've answered your questions. The explanatory variable is going to be the time spent on smartphones because the more time spent on smartphones, the lower the GPA is. It's not a situation where GPA is going to predict the time spent on the smartphones, so that makes our grade point average the response variable. And the second one, how does the amount of time spent doing homework affect test scores? Again, the explanatory variable is going to be the time on homework. The more time you do on homework, the better we're going to expect you do on the test. The test score isn't going to predict how much time you do on homework. So then what we want to do is we want to describe our variables. I know we covered this before. We want to describe our scatter plots that we're going to create from all our data. And we're going to use this acronym DOFS, DOFS. So the first thing to look at is D, the direction. Is it positive, is it negative, or is no direction at all? Then you're going to look for outliers. Are there values that just don't seem to fit the pattern of what we're looking at? We're going to look at form, the F. Is it linear? Is it curved? Is there no form at all? Is it just a scattering of dots all over the graph? And then strength. Is it weak? Is it moderate? Is it strong? Are there dots grouped close together? Are they spread far apart? Are they forming a very distinct line? Is it kind of more of a mesh that's kind of sloping up or down as we go through? Okay, so on the next slide, we're going to practice a scatter plot. I want you guys to take a minute on the graph you have in your notes and figure out what the explanatory variable is, what the response variable is, and then plot all our hours of age and sleep on the scatter plot just to kind of refresh our memory from doing that last week. I know we did a lot of it in Google Sheets. Let's see if we can do a small one on paper by hand, because I do want to work on something like that as we go through our projects. So take a few minutes to do that. Okay, well, now that we've got that done, our explanatory variable again is going to be age. Hours of sleep doesn't predict somebody's age. Age is going to predict how many hours of sleep there are. So the response variable is hours of sleep. And when you finish your scatter plot, it should look something like this. So kind of can see how do you do, what does it look like, and then we'll do some more work with this data later on in our presentation here. So the next slide, here's a bunch of examples of what the strength and direction of some scatter plots would look like. Obviously, a strong positive correlation is going to be tightly grouped data, pretty much forming a straight line. Weak positive correlation is going to have some scatter amongst the points, but definitely still seeing that the trend of the plots of all our points is sloping upward to the right. Again, strong negative correlation is tightly grouped together, sloping downward from left to right. Remember, we're reading our graphs always from left to right. A weak negative correlation, again, is going down from left to right, but the points and the spots, so the dots for our data, are kind of spread far apart. A moderate negative correlation, things kind of get grouped a little bit tighter together from the weak one, but not as tight as the strong. I mean, strong positive or negative correlation, it's like you're pretty much looking at the dots are forming the line when you're putting the line of best fit in. It's like right on the dots. And then no correlation, it's the dots have no rhyme or reason. As the x goes up, the values of y are going all over the place. We just never know where it's going to be. Does that make sense? Okay, here's a couple more examples. Here's one where we have what looks like very strong positive correlation, but then we have the one outlier that's kind of off by itself floating. I apologize for my graph. Those two blue dots with a box, I'm not quite sure what those were. And then an example of a clustered one is the one on the right there, which is Old Faithful. The guys are out in Yellowstone National Park's eruptions in minutes over the amount of time they erupt versus the amount of time between the eruptions. So you can see as if the amount of time is kind of closer together or shorter, the eruptions are smaller. As the amount of time increases, then the eruption time kind of groups together, and there's like two definite sweet spots for amount of time, and then there's a spot in the middle where it's kind of not really as prominent of a where there aren't really a lot of eruptions between 3 to 5 minutes when they're in the 60 to 80 minute range. Like, it seems like all the eruptions are either close together in under an hour or more closer together an hour and a half. Okay, correlation. Correlation is the quantifiable measurement of the direction and strength of the linear relationship. When we kind of went back and looked at our graphs, we can describe what it looks like, but we can definitely quantify it with a number, so that we're not just kind of given, it appears to be a strong positive correlation or a weak moderate or moderate negative correlation. We're going to put a number on it that'll definitely tell us whether yes, it's strong, no, it's weak, or there's no correlation at all. So, some facts. A perfect linear relationship, which is a strong, absolute, perfect correlation where X is definitely predicting Y all the time, your R value is going to equal +1. R is the letter that we use to represent correlation. A perfect negative linear relationship then obviously is going to be -1. All your R's, all your correlation coefficients are going to be between -1 and +1. They're never going to be 2. They're never going to be -4. They're always going to be somewhere between 1 and -1. Correlation, like we say, it makes no distinction between the variable and the response variable. Excuse me. So what does that mean? What it means is if we're to flip the X and Y variables, the correlation coefficient is going to be the same. It doesn't matter what variables on the X or Y axis. We're going to get the same R value when we calculate what it is with the equation that we use to calculate that. R doesn't change the units of measurement, so it's really, the R has no bearing on what units of measure we're using. We could use inches, we could use meters, we're doing time, we can do seconds, hours, minutes, because what we're doing is we're standardizing the two variables. We're taking the average of all the Y's, we're going to figure out a value for each individual Y point based on the average and the standard deviation of the Y values. We're going to do the same thing with the X values. So we have like a standardized number rather than the plot of where the variables are. And then what we always say is correlation does not imply causation. We're not saying that X causes Y. We're not saying that your age causes the amount of hours you sleep. What we're saying is that there's an association. The only thing that can determine causality between two variables is a well-designed experiment. That's the only way to do causation. Correlation is only shown in association. It appears that the amount of hours you sleep affects the scores you get on tests. Some more facts. Say both variables must be quantitative. They both must be something that we can record as a number. You can't do a category. You can't do a comparison between the color of somebody's hair and how tall they are. It doesn't work that way. You can do height and weight like we've done before. You can do age and speed somebody runs. You can do total hours spent in the gym, what the amount of weight they can lift, things like that. You can't do a qualitative descriptive variable and a number variable. And we only look at, well, we're only going to look at a linear relationship. There is correlation between some geometric changes. We're just not doing that because it's a lot harder to figure out, and we're just not working on that. We're going to stick with the linear relationship to predict the linear correlation. I say a correlation close to 1 or -1 doesn't guarantee that there is a linear relationship because we need to see a scatter plot. We need to see what the shape of the data looks like. Is it curved? And then we're talking about the geometric changes and the geometric relationships, and that's something that we don't want to deal with in our stuff. And then it's not resistant to outliers. So big outlier numbers can affect the correlation because the correlation coefficient is calculated by taking each individual observation and subtracting the mean from it. So if you have an outlier in the observation, now your mean values are thrown off. They're higher than you would expect, which is causing the correlation coefficient to get thrown off so that it doesn't quite work out. When we talk about the coefficients and the positive and negative relationships, you've seen that the values go between 1 and -1. So obviously I would think a positive correlation or positive relationship, your R value is going to be greater than 0, getting close to the +1. So therefore your negative relationship is going to be less than 0. Well, again, here's some more examples of strong directional linear relationships with the R values. You can see the first one, it's an R of 0.93, so we're pretty close to being a perfect linear or perfect correlation with our R values. So you can see we could definitely see there's a point where you could definitely put a line through there. As the R values get lower and lower, the correlation spreads out where you can kind of maybe sort of see we could put a line in there. The middle one on the top row appears to be sloping slightly positively upward from left to right, but really you don't know what it's going to be. And same thing on the last one, the scatter is quite spread out, so it's hard to see where the line of best fit's going to be, which we'll talk about tomorrow. And then the negative correlation, again, it's the exact same thing. So we've talked about what the correlation coefficient is and how to calculate it. So we're going to be calculating it. Here is the equation for it. Again, we're in statistics. The equations are kind of getting messy. I'll kind of explain what each part of it is as we look at it. So what you're looking at here is the R value. Again, we're saying that stands for the correlation coefficient. That's the variable we use for it in math. We're going to multiply by the 1 divided by the number of observations minus 1 again. Again, we don't want to use, we always want to take one description, one observation off when we're doing our calculations this way, just to get a better reading of the data. Again, we get the Greek letter sigma again, which we know stands for the summation. So we're going to add together a bunch of numbers to get one big number that we're then going to multiply by that 1 over r minus 1. And then when we look at it, we have two numbers in parentheses, so we're multiplying these values together. And what you're going to do is you're going to go through and take and find the average of all the x values. Then for each individual x value, and then when you find the average of the x values, then you're going to go through and find the standard deviation. So again, it's not something that we really want to crunch by hand. I am going to have you do it once during this presentation just to practice it, but I'm not going to have you do it all the time. When we look at that, you've calculated the mean and the standard deviation. Now you go back, and for every individual value of x that you have, you're going to take that value of x, you're going to subtract out the average, and you're going to divide by the standard deviation. So if you have 5 data points, you're going to do it 5 times. If you have 20 data points, you do it 20 times. If you have 1,000 data points, it has to be done 1,000 times. That's why, again, we get into the software, using software. Then you do the exact same thing for the y's. Figure out the average, that's the y bar. Figure out your standard deviation. If you remember what that was, look back at the notes from the last chapter. Everybody did pretty well on the test trying to figure it out, so it was good. Just make sure you're getting it perfectly. And then take the difference between every observation, the mean, and divide by the standard deviation. Does that make sense? No, it's a lot of work. Again, I'm going to have you do it once during this lesson, and then from there you're going to go on and we're going to use spreadsheet stuff to do it. Again, we're asking, is there anything familiar? And what it looks like is the z-score. If you remember when we were trying to figure out z-scores, we took the value of the x that we have, subtract the mean, and divide by the standard deviation. So that's really what the correlation coefficient is. We're taking the z-scores for the x and y values and we're multiplying them together. If that helps make sense with that. Okay, now I talked about what was I going to have you calculate it. So if we go back to the data that we had for our scatter plot, it's the same data. What I want you to do is go through and try to figure out the correlation coefficient. I know it's going to take you a while. So like I said, the video is going to pause. I'm going to have you try to type in what you got for an answer when all is said and done. And then I'm probably going to see if I might even have you upload your work. I'll decide by the end of the demonstration here to figure that out, but I might just kind of let you do it, because I'm going to give you the opportunity, if you want, is to go on Google Sheets and try to figure out, using Sheets, how we can kind of work it to figure out this information for us, because you got to figure out the average for age, you got to figure out the standard deviation for age, which I've shown you how to do. We've done it in the past in some of the work we've done before. Then you need to find, for every value of age and hours of sleep, you have to do that difference of the value minus the mean divided by the standard deviation. So you can kind of plug all this into a spreadsheet and it should pump out the correct correlation coefficient when you're all said and done. If you even want to try to figure out, there's probably a formula within Google Sheets somewhere that'll do it all for you. I'm going to put it on you to try to figure out how to do that on your own time now. But again, like I say, pause the video, kind of plug in what the correlation coefficient is you think it is, type your answer into Edpuzzle, and we'll go on, and I'll definitely go over it some other time, the actual work for it. All right, so now that you got that, here is what you should have got. You should have gotten a correlation of negative 0.98301. So the data that we're looking at is a very strong negative association. Um, Again, if you kind of go back, it's the data we did the scatter plot for. If you kind of go back and look at it, not quite sure it's straight. So it's one of those things where it's probably we could do it as a linear regression, but I'm not completely sold that it is. So we'll kind of look at it as we go through and do that. But question then is, what to tell us about? I actually just did that for you. It's negative, it's close to -1, and indicates a very strong negative association, um, meaning that the older you get, the less hours you're going to sleep. All right, so everybody, that's the end of the presentation. Um, Hope everybody kind of understands that. Again, we'll kind of go over it a little bit more. If you have any questions, send me an email. I'm not going to do any homework on this tonight because it's a lot to kind of take in. But what I'll work on once I kind of go over them is all the scatter plots we did um, last week sometime. We're going to go through and try to figure out from all that data, we're going to try to figure out correlation coefficients using Google Sheets. So that'll be what we'll work on kind of with Friday's lesson and then the new stuff on Friday. So everybody have a good day, and I will talk to everybody on Friday.